So yes, in this presentation, we will give you a little bit of an overview of some of the work that's happening in SusCoRD work package 3. So in this work package, we're looking at coatings and substrates in great detail using the advanced characterization techniques that are available at the university. So I'll first briefly introduce the work package, and then Zhou will give a bit of a broader overview. And then one of the researchers, Reza Ahmad, will give a bit of an example of what is going on in one of the particular projects that we have running. So to start off with, so obviously, I mean, you've heard about AkzoNobel before. Paints and coatings company making paints and coatings for many different applications, and all of these coatings, once they've been applied onto a substrate, they have a finite lifetime. And quite often, the substrate is actually a metal. And if then the coating fails, so it's reached the end of its lifetime, it doesn't protect the substrate anymore. And what you get then is corrosion. And you see here a couple of examples of that. So ultimately, what we want to do is want to be able to design coatings with a longer lifetime. And we want to be able to really select the best sustainable raw materials to be able to do this. And we want to be able to formulate coatings effectively and sustainably. So to be able to do this, we really need to understand these coatings in quite great detail. And they're really quite complex systems. So you've seen a little schematic here, a cross-section of a coating microstructure. You can kind of see how complex it is. I mean, in this example, the substrate is a metal, but there's other types of substrates that we apply to as well. And you can also see that the coating really consists of many different components. Now, these systems, they get exposed to an external environment. So they get exposed, for instance, to moisture, to UV radiation, to salt. And over time, they will degrade slowly. This happens very, very slowly, and so it's very difficult to study these changes that happen in these materials, and specifically the underlying microstructural processes. So we really want to understand these further, and understand also how we can slow these down further. So really what work package 3 is aiming to do is to provide new microstructural insight to help improve the performance of coatings. So in one part, it's looking at the microstructure of the coatings and investigate how the microstructure of the coatings affects the aging and the degradation of these materials, but also to look at the substrate and the pretreatments being applied in the substrate before the coating gets applied onto it. So how this pretreatment then relates to the lifetime ultimately of the coating that's being applied onto it. And this will help us in AkzoNobel a lot to come up with improved strategies to formulate paints and coatings. And so I'll now hand over to Zhou, who will give you a bit more detail.
Okay, thank you, Nick. Yeah, as Nick just mentioned, what we want to do within this work package, we want to look at the microstructure within the coating and the interfacial region between coating and the substrate. Try to monitor the microstructure evolution when the coating and coating system is exposed to an environment. Then correlate the microstructure evolution to coating property and to performance. So we will look at the compositional change, morphology change, and the structure change over all length scale in 3 dimensions. So here we have an example showing the microstructure change within the coating. So as you can see here, we have color-coded the pigments of different composition in different color. So the matrix now is transparent. So by comparing the images before and after exposure, you can notice the change in microstructure. So specifically what we found some pigments which has been dissolved during exposure the result is such, then you have porosity in generated within the coating. Then over time, we find a connected network of velocity porosity can be established, which provides the faster transport paths for certain species to be transported to the location which is needed to provide active corrosion protection. So if you look at active, effective corrosion protection over service life, the ideal situation would be such. You would like to have the inhibitor which can provide corrosion protection to be leached out at a controlled rate. You don't want to have such species be leached out possibly after 1 month. And also, you would like to have the situation, the transport path is available, therefore the transport is fast. If there is a defect area, the effective species can be quickly transported to the location which is needed and reach a critical concentration. So therefore, a protective film can be formed. So based on what we have found that the connected network of porosity is important for transport. So possibly from this project for future coating formulation, we can consider, can we have a mixture of different pigments with different solubility? And for certain pigments which can be dissolved fast, therefore you can quickly establish a transport network. And for those effective inhibitors, we should have a controlled dissolution and the leaching rate. This is one example. Another example is the coating, marine coating, which has been exposed to a service condition for a long time, 18 years. What have been found? After 18 years in service, the barrier property, the resistance of the coating has been reduced to a degree, although which still meet the requirement for industry standard. So what we have done, we try to create the reduction in resistance in barrier function to what happened within the coating, to what has changed for the microstructure. So from the images you can see, actually the change, the reduction in resistance is related to the thinning of the coating and the damage within the outer region of the coating. And we managed to go a step further. We have found thinning and the damage is occurred in such a way which is related to cracking within the pigments and also desponding between pigments and the bender. And also we have found different pigments can give you different resistance to fracture. So for example, aluminum flake is more resistant to mechanical cracking compared to other pigments such as tack. And also within this project, what we have found, if you have a situation, the pigments is oriented as in such a way which is parallel to the coating surface, and as you can see here from this schematic diagram, the propagation inwards, the penetration rate can be significantly reduced. So therefore, if we can have a situation of pigments being oriented parallel to the surface, so consequently you can have a situation that resistance can last for longer. So for future formulation, again, what can we do in terms of arrange for the alignment for pigments within the coating? Another example is to look at the interface between coating and the substrate. Specifically to look at how can we modify the substrate to make sure we have desired interface interaction. So here is an example showing coating on aluminum alloy wheels. And we know when we have a pretreatment, quite often we can achieve better performance. From this project, what we have found, when you have a pretreatment of what you have done to the substrate, you can not only remove the contamination from the alloy surface, you also can remove certain microstructure from the alloy surface, because we know for different alloy fabrication process, depends on how severely you deform the surface region. You can introduce a microstructure which is different from the bulk microstructure, quite often which can give you a more reactive surface. So the pretreatment actually has done a few jobs: remove contamination, remove the more active near surface layer, and also here, as you can see, produced a uniform conversion coating on the surface, which can interact bad with the coating compared to the metallic substrate. So here we have a conversion coating which is only about 20-30 nanometers thick, uniformly formed across the surface. Within this work package, currently we have 7 projects. So I'm not going to go through all the projects. I would like to ask Reza to give us some more details on the project he is working on, and he will show us what he has found.
Thank you, Sharon.
Okay, thank you. Thank you, Sharon, for the introduction. Hello, everyone. So just to start with a brief introduction. So you heard a lot about organic coatings, and as you know, they fail usually spontaneously when they are exposed to the environment. And in order to justify that, it is believed that organic coatings are heterogeneous in nature, and there are regions that usually uptake more environment or less environment compared to the others. And it is believed that these regions can grow in size after exposure to the environment due to the environmental stresses that exist, and form a percolating network through the thickness of the coating and results in the failure. But organic coatings are not only made of polymeric binder and curing agents nowadays. There are several different inorganic and organic fillers, also different additives added, but also we can have different layers of organic coatings there on top of each other. So it is important to understand how all different ingredients, pigments, fillers, additives will affect on this percolating network formation and how they will affect the performance of the coating. So the aim of our project is to understand the structure of powder coating systems and its correlations and its performance as a service lifetime of the coating. And in order to do that, we AkzoNobel provided us one-layer polyester powder coatings exposed on panels, and then they are exposed to the 2 different test environments. One is the continuous neutral salt spray test, and the other one is actually cyclic corrosion test for 4 months and 6 months. So the samples that were exposed to the cyclic corrosion test all showed actually failure after 4 months, and this continued and increased the failures, and eventually after 6 months, in some cases, we ended up having a complete damage of the coating. But the samples which were exposed to the neutral salt spray test, actually, some of the panels showed not significant amount of the corrosion, and only corrosion from the defect when a defect existed on the coating. But also we had the cases that blisters formed on these samples. So let's start the characterizations of the coating by looking at the unexposed panels. So I've used SEM at different accelerating voltage to look at the surface of the coatings. And as you can see, the surface looks like a smooth surface, but when we increase the accelerating voltage, we can see the distributions of the pigments within the coating, which appears to be random. Now, if we look at at higher magnification and zoom in, we can actually see some discontinuities within the top surface of the coating. And in most cases, these discontinuities are associated with pigments exactly underneath the coating. And this is a cross-sections again of a pigment that is breaking through the coating. And as you can see also, there crack exists at the interface of this pigment, which may allow penetrations of environment into those regions. But also the other thing that we observed is formations of clusters through the entire thickness of the coating. So something that we didn't see on unexposed samples is formations of the cracks. However, when the samples were exposed to the environment, especially cyclic corrosion tests, we observed crack formations on the surface while there is no evidence of any blister or anything else. So, and these cracks will propagate through the coating, as you can see here, the crack propagation tips. And we believe these cracks eventually will result in the failure and propagate and reach to the substrate. So there are different stages of crack development, usually involving the crack initiation and the crack propagation. So the crack initiation is a statistical process which actually happens at preferential sites. So where are these preferential sites? One preferential site can be actually the interface of the pigment, a large filler, with the binder. So when the coating is exposed to the environment, and it is under the environmental stresses, the polymer, which is softer, can go through, change its shape, and actually accommodate the stress and change in shape. But the polymer, which is harder, cannot do that. So the interface of this pigment with the binder will actually meet some high concentration and stress concentration point, and then can develop further into cracks that are propagating through the coating. The other example of a preferential site for the crack initiation and development can be actually when at the substrate, when we have a rogue peak or significant substrate variations. At these points, actually, we may have a different the stress field may be different within the coating, and stress concentrations may form and result in the crack initiation. So, for example, in this example, if we look at it at low magnification, we do not see any blister or anything. But if we zoom in, we can see corrosion products are already formed, and also they are filling the cracks. So I think there can be two different scenarios happening here. One is that actually this stress concentration point results in the crack formation, and then the crack propagates through the entire coating thickness and results in allows actually transport of environment to this point and results in the corrosion formation, and then corrosion penetrates into the crack. But there is also another case where that actually the stress concentration may result in the detachment of the organic coating from the substrate at this point. And then we know water and oxygen can penetrate into the coating and come and accumulate at this point, and then corrosion starts. And then crack maybe forms and propagate as a result of the corrosion formation and growth in the volume of the corrosion products. So we believe crack initiation and development can be the reason for the failure of the coatings that were exposed to the cyclic corrosion test. And as you can see here, after that, when the corrosion products form, it may result in a blister formation. And as you can see here, probably we have two blisters which are connected to each other. But the other thing that we observe, first of all, is formations of the crack at the periphery of these blisters, as you can see here, which are now filled also with corrosion products. I will discuss about this a little bit in the next slides. But also we have observed corrosion product depositing at the interface of these fillers. So the question is that how these corrosion products have been able to move there. Are there interconnected cracks there that allows corrosion products to move there and get deposited, or actually corrosion products are transporting and moving through the bulk of the polymer and then get deposited there? So the other thing that we observed is that when we have clusters of particles very close to each other, we can see that the interface, when the corrosion happens, we can see that the interface of these particles we get decorated with corrosion products. So the question is that what is happening at that interface? Is there a gap exists there, or is actually there is a chemical change within that interface that allows more accommodations of the corrosion products? So we try to look at these interfaces by doing some high resolution microscopy at high magnification, and actually we couldn't reach a conclusion. We have seen gap formation which is filled with corrosion products, as you can see here. But also in other cases, we have seen actually that while there is no gap there, but still the EDS map analysis shows corrosion products exist in that interface. So this is something that we are going to do in future and characterize this interface in more details, because we believe there are some details into that interface that needs to be understood. So my next example is actually the data from the X-ray CT that we decided to do use a complete blister to gather X-ray CT data, which is non-destructive, which allows us to see the internal structure of the coating. And actually, so if we assume that the failure happens and then the blister forms and grows, and if we assume this growth of blister is happening uniformly around the failure point, we may expect to see the failure points almost in the central region of this blister. So what I have created here is a video of this CT data that goes through different slices, and then you will see segmentations of the data. And so what you will see are going to be some cracks in the center, and also at the cracks penetrating into the coating, cracks at the interface. But since it's exactly at the center of the blister, the growth of the blister due to the formations of corrosion products may also insert some stress there that cause formations of that crack. So it's not going to be easy to say that these cracks are the reason for the failure. But the other thing that I wanted to focus is that actually formations of elongated clusters that span through the entire thickness of the coating. So if this interface of these clusters of fillers is weak point and allows the immature failure of the coating at that point, then we have seen actually these clusters exist within the center of this blister. So can you play the video? So this is the volume that we are going to look at, then going through the slides through the volume. Actually, there are two large blisters there, and the first one, this pigment appears, but then immediately another pigment appears that goes up, and then there is another cluster over here as well. So these are the two clusters, and now they are also visualized in the segmented data as well. So the two clusters, the corrosion products, and the substrate underneath them. So the other thing that I would like to mention is that, okay, so the failure happens, corrosion starts, the volume of corrosion products expand, and the blister forms. But then what we see from this slice, which is one of the slices of the CT data, is crack starting to form at these 2 points at a specific point, which may indicate a brittle failure of the powder coatings. And actually the CT data showed us that these cracks almost within this specific sample penetrated and covered almost more than a quarter of this blister. And these cracks, by the growth of the blister, these cracks can become interconnected and results in complete detachment of the blister from the substrate and results in a large exposure of the substrate area to the environment. So, so as I said, the blister forms, cracks start to form at the edges of it, and then cracks becomes interconnected. But there is another point here that actually we observed, that cracks start to deviate outward and into the other coating, which may further propagate the damaged area to the coating and results in the failure, complete failure of the coating, as we observed for the panels which were exposed for 6 months to the cyclic corrosion test. And to finish my talk, actually, so electron microscopy and X-ray CT gives insights into what happens on the microstructural level. Cracks form after exposure. Weak points appears associated with pigments or the substrate. Corrosion products are observed to fill some of the cracks and voids. And also we are starting to understand what happens at coating blister failure point. And I would like to hand over to Geraint for the final words.
Okay, thank you, Reza. So as you have seen, now we have a much better understanding of the macrostructure of coatings, and also the evolution of macrostructure, and how the macrostructure evolution is related to the degradation mechanism and the coating failure. We have found the answer for certain questions, but in the process, we also have new questions which we will need to find the answer. So we will continue to work on what we have started. And also now we have a couple of new projects which will look at the new microstructure features which can possibly relate to the performance. For example, as we just showed, the network of porosity is important for transport of effective inhibitor species. And from previous project Reza worked with, we found that the particle volume concentration is important. But what about particle size distribution? If you have the same particle volume concentration, but have different particle size distribution, would that give you a different performance? This is the focus of one of our new PhD project. And also, Stuart just mentioned, he said, good adhesion does not necessarily mean good performance. I slightly disagree with that, because for certain systems, the adhesion is important. For example, if you have a substrate which have a certain microstructure feature is sensitive to the environment, so that means it's only this part of microstructure is exposed to the electrolyte, corrosion can occur. So then adhesion is important. If you have good adhesion, that means the interface is protected. Then you prevent that susceptible microstructure to environment. So that's why we have a new project on looking at the adhesion promoter, the influence of adhesion promoter on the coil product on coating performance. Okay, thank you.